All right, so we'll be going over exam level question number 2, MSD Radix Sort. So in this question, they're asking us to implement MSD Radix Sort. What do they give us? Well, they give us some nice skeleton code and as well as some methods to use when answering these blanks. But before we hop into any of them and in any of that, let's go ahead and go over some intuition about what radix sorting is. Well, radix sorting, instead of comparing values, we're going to be comparing the values of each digit. So what we're going to be doing is we're going to be going digit by digit and comparing them and sorting it that way. So for MSD radix sort, we're going to start at the most significant digit, hence MSD, and we're going to continuously increment our index to the right until we get to the least significant digit. So over here, we notice we have the very first iteration of MSD. What do? We choose the most significant digit, and then we sort by that most significant digit. Notice how all the lowest significant digits, as in the ones over here, get pushed to the top. The fours are grouped together and put right below the ones, and finally we have 7 and 9. But this doesn't fully sort our entire array or our entire list of items. There's more that we have to do. And what do we have to do? Well, we have to partition and recurse. What does partition mean? Well, partition means we're going to be grouping all our elements that are equal in the digits that we are comparing. So we notice in this green bubble, we are comparing 121 and 120. The current digit that we're comparing is the most significant, and the ones are the same. Therefore, we're going to group those two together and partition them. And then we recursively call MSD on this group. Notice how for 452 and for 435 in this purple section, we have the same thing. We group the elements that are equal at the current digit that we are comparing. 452 and 435, well, we're both comparing the fours, and so we're going to group those together and call radix sort on those. What happens when we call radix sort on those? Well, before we get to that, let's go ahead and look at 789 and 950. Notice how they don't share any digits, or they're not equal to any other digits that we're currently looking at, in the index that we're currently looking at, rather. So what do? Well, we just group them up with themselves and recursively call MSD radix sort. When we sort one element, what happens? Well, one element is, well, trivially sorted, right? And so we can just return that element. Hence, we have this long arrow putting it into our answer, like our final item sorted array. But say it's not just one item. Say it's more than one item, and those items are different, just like we have in our purple section. What do? Well, we're going to increment our index at which we're checking the digits. So in this case, we're going to be checking the middle digits and sort via those. Well, what happens? The 2s get pushed to the top. They stay the same. And the 3 and the 5 flop. All right. So notice how we're going to group the 2s together. Why? Because the current index that we are working with, they share the same digit. They have the same value of 2. And so we're going to group those together and recursively call MSD on them once again. But for this other section, we notice that they are not equal. And so we're going to group them up with themselves and go ahead and call MSD radix sort. Well, since they are only one element, what's going to happen? Well, we're just going to return it and add it to the list. And that's why we have this arrow pushing it to the rightmost side. Then we have finally one recursive MSD radix sort call. And so what's going to happen? Well, we got to increment our index once more, and we're going to be looking at the third or the least significant index. We're going to sort according to that index. So 0 comes before 1. We're going to put 0 above 1. And we have 120 and 121 sorted. Notice how these do not share the same value at the digit we're currently comparing. They're 0 and 1, they're not equal. And so what do? Well, we're going to group them up with themselves and go ahead and return them once we hit our base case, that being their size of 1. So now with that little bit of intuition on how MSD Radix Sort works, let's go ahead and hop into an implementation. So we're given this skeleton code. Notice how we have two methods called MSD. The only difference between the two is that we have this extra index over here. So this implies that we are most likely going to be calling our other MSD, passing in some sort of start index. The question is, what's going to be that start index? Well, with MSD, we're going to be starting at the most significant digit. And that's what we saw in our example over here. We started at the most significant digit, or the 0th digit. So we're going to be passing in 0 for our index. Now for the base case, when did we just return our item? Well, we returned our item, as we saw in our example, when we hit an item or a grouping of size 1, right? We have 120 and 121 and 435 down here, and 452 and 789. These are all groupings of just one element. And if they're groupings of one element, then we have nothing else to compare it to, therefore it's sorted. And so we just want to return it. So how do we represent them in our code? Well, we say if items.size is going to be less than or equal to 1, well, then we want to just return the item. That means we are guaranteed at least or anything lower than 1 item, right? If there's 0 items, well, there's nothing to sort. All right. There's one other case that we have to go over. What happens if there's duplicates? Let's take a look. Say we had a duplicate of 121 and let's say we just were working with 2 elements, right, of that duplicate. So we start comparing our very first elements, right? We have the 1 and the 1. Sorry, let me just delete this really quickly. These create a grouping, right? We're going to partition them together because the current digit that we're looking at, which is the most significant digit, they're equal. And then we're going to increment our index and call MSD Radix Sort. Then we're going to get to the 2s. Notice how, again, they are equal. And then we're going to get to the 3s. We're going to increment our index, or the 3rd index, right? Or the 2nd index, the least significant digit is another way to put it. Once again, those are equal. And so we're going to group them together according to our partitioning rule and call MSD Radix Sort on them just once more. And when we call MSD Radix Sort, recursively, we noticed over here, we'd increment our index at which we look at, right? At which digit we look at. And so if we increment our index once more, well, our index is going to be past it, right? We never hit our base case of just, is our grouping less than or equal to 1, right? This is less than or equal to 2. And so our index has surpassed our length of our elements. When our index has surpassed our length of our elements, we notice that all the elements that we're working with are going to be equal. So 121 and 121 have to be equal if the index has passed them, and they're still greater than the size of 1. All right, so how do we put that? We're going to say or. Or if our index is going to be greater than or equal to the length of the element, right? We were looking at the length of the element over here. So how do we do that? We say items dot get at 0 dot length. Why did I say get at 0? Well, once the index is past this, we are guaranteed that all of the elements are going to be of same length. Therefore, we can just call arbitrarily the 0th index. The 0th index, rather. Okay, so with our base case established, let's go ahead and move on. What was the very first thing we did? The very first thing we did was sorted the most significant digit. And then we worried about all of our ifs and partitioning and recursion and all of that complicated stuff. But first, what did we do? We sorted it according to our given index that we started at. And in this case, we happened to start at the most significant digit, or index equals 0. So let's go ahead and reflect it in our code. We're given this stable sort down here. This stable sort does exactly that. When we call stable sort and pass in some item and our index, what we're essentially doing is this. This is passing in our index as 0, and we're going to be ordering all of our elements according to their current digit and their value, right? So in this case, our current digit that we're going to be working with is the most significant digit, and we're going to be sorting that according to that. Cool. So that's how we got this part. Now we can worry about all of these crazy ifs and whatever is going to happen. But before we do that, let's go ahead and notice that we define something called start equals 0, or is starting at 0, and we're going to be incrementing through our end, right? So we've also created an end. Let's go ahead and work with those then. We're going to take our start and point it at index 0, just how it's defined. And same with end. End points at index 1 in our for loop. So we notice that they're currently pointing at the same, or they're currently pointing to elements that are in the same partition, right? The digits that we're currently comparing are the same. So do we want to partition here? Well, not yet. We don't know if the next element is going to be part of that partition. So let's go ahead and increment our end just once more. Now we notice, comparing our start to our end, that the digit that we're currently working on, which is our most significant digit, it's not equal anymore. We have 121 and 452. The 1 is not equal to the 4. And so what does that imply? That implies that we've iterated already through our entire partitioned group. We've iterated over everything that we need to group up and recursively call MSD Radix Sort on and all of that. So let's go ahead and implement that. So we say if our item dot get, well, we're getting it, our very first element at start. And the character at index, right? We have to compare the current index that we are on when we are partitioning. So we want to say, hey, if this is not equal to the same index at the end, well, that means we've iterated through our entire grouping of the same element. Therefore, everything before the end, and including the start, we want to call MSD Radix Sort on. That rings a bell. We're essentially grabbing a sublist, right? And so let's go ahead and use this hint that they give us, the sublist. We're going to define a new variable. Let's call it sublist. And we're going to say items.sublist, where we're going to be passing in our from index. Well, we want to get our sublist starting at this start element and ending at our end element, right? Our end points to this 452. And you might ask, hey, Dylan, won't that 452 be included? No. Well, our sublist keeps start as inclusive and end as exclusive. So we're just going to create a sublist of 121 and 120 and not 452, right? So the element just before we hit end. And so look at that. We created a sublist of all the elements that should be partitioned together, all the elements that share the same value at the digit we're currently exploring. Now, what do we do with that? Well, we noticed over here, we incremented our index and recursively called MSD Radix Sort until we hit our base case and returned it. So let's think of how we can do that. Once it's returned, we will have to add it to our final answer, right? Our final returning list. And that's what we have defined over here. So we're going to say answer.add all, add all of, what are we passing in? Well, we have to call MSD on our sublist. And what happens to our index? Every time we've called MSD, we've incremented our index. Notice how we started at the most significant digit, then we're starting at the middle digit, and finally we're ending at the least significant digit. So every time we call MSD Radix Sort, we're incrementing our index, because we then have to sort by the each index starting from the most significant digit all the way till the end, or the least significant digit. Now, what's this last line? Well, we need to figure out, once we've partitioned once, how can we find the rest of our partitions? So say we've hit this if statement here, right? We've partitioned the green bubble out. Now, how are we going to get that partition of the 452 and the 435, or that purple section? Well, if we set end and start equal to each other, they're pointing at the same place. Well, we're not going to enter our if statement, right? Because the digit that we're currently working on, 452, is going to be equal, right? The end and the start, the digit that we're currently working on, is going to be equal. So what do? Well, we're not going to enter our for loop, and we're going to move our end down. Notice they are still equal at this case. The current digit that we're working on, which is the most significant digit, those being 4, they're both still equal. So we're not going to enter our for loop, or if statement, rather. And so what do? We increment our end just once more, and bam, we found the partitioning of purple. So what did we notice was the key? We're essentially going to set our start to our current end. And we're done. Except there's one thing we were missing. What happens when end points to the very last element? And what happens if start also points at that very last element? Right? We've partitioned this orange part out, and we're going to set end equal to start. And now we're going to have a little bit of a dilemma. We're going to say, hey, increment our end and point it, increment our end and point it to the next element. But do we have a next element? Oh my God, it's stuck. But do we have a next element? No. And so we're going to get an index out of bounds error. So how do we prevent that? Well, if we say end is pointing to our very last element, then partition that last element. We're done, right? There's no more elements that we need to look for to partition. And so let's add that little extra condition. So we say if our item, or rather, let's say if our end that we're working at is going to be equal to items dot size, or it's at the very last element, then we need to partition and we are done. So this was the final implementation for question 2 on discussion 14 exam level. Yeah, I hope that was helpful.